Imagine the Arctic today, a harsh land blanketed in ice and snow where animals like polar bears, seals, and Arctic foxes struggle to survive in the biting cold. This region is often described as a vast icy desert, a desolate and isolated wasteland. However, the picture of the Arctic in the distant past was completely different, offering a striking contrast. Tens of millions of years ago, this northernmost region was a lush, green, temperate forest where giant dinosaurs and other strange creatures roamed freely. This isn't a futuristic vision or a mythical tale, but a reality proven by a wealth of fossil evidence. The massive difference between these two images isn't just a change in temperature, but a complete transformation of a biome from a thriving forest to an icy desert. This challenges conventional perceptions of the polar regions and highlights Earth's capacity for extreme climate shifts throughout geological history. Studying this period provides a natural laboratory to explore how life adapted to extreme greenhouse conditions, which could be useful for understanding current climate change. To explore this unexpected world, we'll travel back in time to the late Cretaceous period, which lasted from about 145 to 66 million years ago. This was the final period of the Mesozoic era. The age of dinosaurs, and scientists have identified it as the stage with incredible evidence of life in the Arctic, specifically dinosaur and other animal fossils found in the Prince Creek Formation. Alaska, dating back about 73 million years, represent one of the most important sites in the world for Mesozoic vertebrate fossils in the Arctic. The Cretaceous period is known as one of the warmest periods in Earth's history. The global average temperature was about 18 degrees Fahrenheit higher than it is today, and atmospheric carbon dioxide concentrations were 2.5 times higher, reaching about 1,000 parts per million. This created a strong greenhouse effect, which led to the absence of continental ice caps at the poles, allowing forests to thrive. The Arctic ecosystem at the time was a highly diverse and productive circumpolar ecosystem with no modern analog. The global warming during the Cretaceous due to high carbon dioxide levels eliminated polar ice, allowing temperate forests to flourish at high latitudes, creating a completely different habitat and paving the way for the diversification of animal species. This is why the late Cretaceous was chosen as the most dramatic period to explore, because it represents an unexpected prehistoric paradise, where life developed unique adaptations to challenging environmental conditions. The strange climate and landscape of the Cretaceous Arctic. In the late Cretaceous, about 70 to 73 million years ago, the Arctic region, including Alaska and Siberia, had a significantly milder climate than it does today. The average annual temperature in northern Alaska is estimated to have been around 44 degrees Fahrenheit, much warmer than the current average of 10 degrees Fahrenheit. Ocean temperatures may have even reached 95 degrees Fahrenheit. This suggests that the Arctic was not a land of permanent ice, but an environment capable of supporting diverse life. However, a warmer climate doesn't mean the ancient Arctic was completely without winter. Winter temperatures could still drop to 14 degrees Fahrenheit, cold enough for regular frost and snowfall, though it was likely a thin layer insufficient to permanently impede plant growth. There is even evidence of a severe cold snap lasting about 6 million years during the Cretaceous, with average ocean temperatures dropping below 46 degrees Fahrenheit. The existence of snow and freezing temperatures in winter, even during a global greenhouse period, shows that Arctic organisms not only face the cold, but also significant temperature fluctuations requiring flexible adaptations beyond just living in a warm environment. This implies that the ancient Arctic flora and fauna not only needed to adapt to high average temperatures, but also to endure periodic cold snaps, frost, and snow. The biggest challenge for life at high latitudes was not the temperature, but the unique light cycle. Just as today, the ancient Arctic still experienced several months of continuous darkness polar night and several months of continuous sunlight polar day. This period could last for about 5 months each season. During the polar night, with no light, plant photosynthesis ceased, leading to a scarcity of food for herbivores. The extreme light cycle was the key environmental factor shaping the ancient Arctic ecosystem. Even when it was warm, the Arctic couldn't sustain life like the tropics due to the lack of light for a significant part of the year, making light the ecological bottleneck. The Cretaceous Arctic was covered in dense temperate forests, not ice. The vegetation primarily consisted of a mix of deciduous conifers, ferns, and both angiosperms and gymnosperms. The diversification of angiosperms began in the early Cretaceous around 130 million years ago, and they became dominant by the mid-Cretaceous. These trees had adapted to survive the changing light conditions. The coniferous forests in the Arctic were mainly deciduous, while in the Antarctic there was a higher proportion of evergreens. Deciduous trees had an advantage over evergreens in surviving the polar night in the Arctic, as they could completely stop photosynthesis and minimize water/energy loss. This shows a sophisticated evolutionary adaptation to the extreme light cycle, optimizing energy and resource use in a unique environment where life had to turn off and on seasonally. These plants were able to hibernate and store energy, starches, oils during the 24-hour summer sunlight to survive the long winter. The growth rings of fossilized trees show a clear difference between early wood fast growth in the summer and late wood very little growth in the winter, reflecting an adaptation to the seasonal light and temperature cycles. The table below summarizes the differences in climate and landscape between the Cretaceous and present-day Arctic. This table helps readers easily visualize the amazing differences between the ancient and modern Arctic, reinforcing the idea of an unexpected prehistoric paradise that we are exploring. Despite facing unique challenges like prolonged polar nights and cold winters, the Cretaceous Arctic was home to a diverse and rich ecosystem of animals. These creatures developed incredible adaptations to survive and thrive in this circumpolar environment. Here are the strangest and most notable inhabitants of the prehistoric Arctic. Edmontosaurus, the giant migratory herbivora. Edmontosaurus was a huge hadrosaur or duck-billed dinosaur and one of the most common herbivorous dinosaurs found in the ancient Arctic. Their fossils, along with those of Pachyrhinosaurus, were discovered in Alaska in 1961. These ancient animals are thought to have lived in large herds, possibly numbering up to 40,000 individuals. To survive the harsh Arctic winters, Edmontosaurus developed a unique survival strategy: migration. Every year, these enormous dinosaur herds would travel south before winter arrived, seeking warmer lands with more abundant food. However, some herds may have stayed in the ancient Arctic to nest, lay eggs, and incubate them during the cold season, showing a flexibility in their behavior. When winter came, the growth of Edmontosaurus slowed down significantly due to the cold weather and lack of food. This slowdown is clearly visible under a microscope when examining their fossilized bones, similar to counting tree rings to determine age and living conditions. This indicates that despite their ability to migrate, individuals who remained still had to face difficult living conditions. Fossils of young dinosaurs, especially from the Hadrosaur and Ceratopsida groups, are found in large numbers in the Colville River, proving that some juveniles were unable to survive the cold environment. In the warm season, as temperatures rose, the herds of Edmontosaurus and Pachyrhinosaurus that had migrated south would begin to return to the far north. Their goal was to find food after many months of winter. The land once covered in ice had now transformed dramatically into a lush, fertile place like a paradise to them, thanks to 24-hour sunlight that triggered vigorous plant growth. However, to reach this paradise, these ancient animal herds faced challenges that were far from easy. They had to contend with predators like Nanuqsaurus and Troodon, which were ready to attack weak or isolated individuals. This led to a remarkable cooperative behavior. Edmontosaurus and Pachyrhinosaurus may have moved together in mixed groups to enhance safety, similar to how zebras and wildebeest migrate in the Serengeti today. Edmontosaurus had better eyesight to detect danger, while Pachyrhinosaurus had greater physical strength to fend off attacks. This cooperation shows a complex survival strategy where different species used each other's strengths to increase their chances of survival. Pachyrhinosaurus, the thick-nosed giant. Pachyrhinosaurus was a large ceratopsian or horned dinosaur that lived in the forests and plains of North America during the late Cretaceous from about 71 to 68 million years ago. Instead of sharp horns like Triceratops, Pachyrhinosaurus was notable for a thick bony structure over its nose and an elaborate bony shield at the back of its head. They could reach a length of 16 to 26 feet and weigh over 2 tons. Fossil evidence indicates that Pachyrhinosaurus had social behavior with bone beds containing multiple individuals, suggesting they lived in herds. Like Edmontosaurus, Pachyrhinosaurus also undertook annual migrations north in the summer to take advantage of the abundant food sources at high latitudes. This journey was not easy, with dangerous predators lurking. Their presence in the Arctic, along with Edmontosaurus, shows the incredible adaptability of these herbivorous dinosaurs to a circumpolar environment. The ability to migrate long distances up to 1,600 miles was a crucial strategy that helped them avoid the harshest conditions of the Arctic winter. Troodon, the clever predator of the polar night. Troodon was a small but formidable carnivorous dinosaur or theropod, notable for its large eyes and a brain that was relatively big for its body size. Troodon fossils are found in abundance in the Arctic region, especially in the Prince Creek Formation, Alaska. Paleontologists have found tooth marks and bite marks on Edmontosaurus fossils at the Prince Creek Formation that are a good match for the shape of Troodon's teeth, suggesting they were common predators in the Arctic. One of Troodon's unique features was its large, forward-facing eyes similar to modern birds of prey. This allowed them to see clearly in low-light conditions, which was particularly useful during the long months of polar night in the Arctic. Like their close relatives in the Troodontidae group, Troodon may have had feathers to keep their bodies warm in the low temperatures. Interestingly, Arctic Troodon had a larger body size compared to their relatives in the south. Evidence from fossil teeth shows their teeth were twice as large, and it is estimated that these ancient animals could reach a length of 13 feet. The larger body size may have helped Troodon maintain its body temperature in the cold climate, which is consistent with Bergmann's rule. Bergmann's rule states that animal species in colder regions tend to have a larger body size to reduce the surface area to volume ratio, thereby decreasing heat loss. However, applying Bergmann's rule to cold-blooded reptiles like dinosaurs is still a topic of debate among scientists. Another explanation for the larger size of Arctic Troodon is the more abundant food sources and the lower number of other predatory dinosaurs, especially tyrannosaurids, in this ecosystem. Troodon is believed to have been an omnivore or a predator of smaller prey with weaker jaws than larger predatory dromaeosaurs. Troodon's ability to nest and reproduce in the Arctic has also been studied. As brooders, they were less dependent on external heat sources to incubate their eggs, allowing them to nest in a variety of environments, including the Arctic. Nanuqsaurus, the Arctic's miniature T-Rex. Among all the dinosaur fossils found in the Arctic, one species stands out that researchers named Nanuqsaurus. The name means polar bear lizard, inspired by the modern polar bear. This is one of the known tyrannosaurids that lived in a cold climate. What's unique about Nanuqsaurus is its significantly smaller body size compared to Tyrannosaurus rex or other tyrannosaur relatives in the south. This ancient animal was only about 20 feet long and 6.5 feet tall, looking like a lighter version of a T-Rex. This smaller size may have been an important adaptation to reduce energy needs in an environment where food sources could be scarce in winter. Fossils of another tyrannosaurid species found in China still had feathers on their bodies, showing that tyrannosaurids were not always scaly depending on their habitat. Therefore, researchers speculate that Nanuqsaurus also had feathers on its body, which helped it withstand the rather cold weather. No one knows for sure what caused Nanuqsaurus to be smaller. However, finding numerous fossils of juveniles suggests that Nanuqsaurus did live in a very harsh environment where only a few could survive to adulthood. The irony is that Nanuqsaurus, this powerful predator, seems to have endured the harshness, not out of compulsion but by its own choice. Paleontologists conclude that these dinosaurs did not migrate south or to warmer regions when winter came. Instead, they chose to stay in the cold, dark environment year-round, along with Edmontosaurus and Pachyrhinosaurus. Nanuqsaurus hutchisoni, a tiny ancient marsupial. The Cretaceous Arctic wasn't just the kingdom of dinosaurs. Paleontologists have discovered a new marsupial species, Nanuqsaurus hutchisoni, that lived north of the Arctic Circle about 69 million years ago. This is the northernmost marsupial ever found. Nanuqsaurus hutchisoni was tiny, only the size of a thumb or a house mouse, and probably weighed less than 1 ounce. This animal likely ate insects and may have lived underground. This is especially important because it shows the extraordinary adaptability of a small mammal to the harsh conditions of the polar night. Nanuqsaurus hutchisoni had to survive 120 days of darkness each year with average temperatures around 43 degrees Fahrenheit. Its ability to live underground may have helped it escape the cold and find food during times of scarcity. The discovery of Nanuqsaurus hutchisoni, primarily through about 60 tiny sand grain-sized tooth fossils from the Prince Creek Formation, Alaska, has painted a more detailed picture of the flora and fauna that once thrived in northern Alaska. This marsupial, along with other unique dinosaurs, shows that the ancient Arctic was an evolutionary center where endemic species developed to fill unique ecological niches. Ancient birds, the pioneers of polar nesting. Fossil evidence from the Prince Creek Formation. Alaska shows that ancient birds were nesting in the harsh Arctic region about 72.8 million years ago, long before their modern descendants did the same. This fossil collection includes a diverse group of ornithorhynch birds, relatives of modern birds, along with rare remains of embryos and newly hatched chicks. These findings suggest that some of the earliest modern birds adapted to the extreme seasonal conditions of the ancient Arctic. These birds nested in this challenging environment to take advantage of the short but highly productive summer, which offered abundant food sources and continuous light with a lower risk of predation. Certain bone characteristics such as toothless jaws and fused leg bone structures suggest that some specimens may be close to or within the modern bird group, possibly related to early waterfowl. Unlike the slower developing enantiornithine birds, which seem to have been absent at these high latitudes, and coexisting dinosaurs that adapted to the polar regions, the ornithorine birds were better adapted for hibernation or migration. This may have helped them survive the end Cretaceous extinction event and later diversify. The discovery of nesting evidence at polar latitudes shows that birds began to use the polar environment for seasonal breeding during the Cretaceous long before their modern descendants did. Champsosaurus, the ectothermic crocodile-like reptile. In addition to dinosaurs and mammals, the Cretaceous Arctic was also home to other reptiles, including Champsosaurus. Champsosaurus was an extinct crocodile-like reptile believed to have lived in environments similar to modern crocodiles, meaning in freshwater. What's surprising is that Champsosaurus was an ectotherm, meaning it depended on the surrounding temperature to regulate its body heat. The discovery of an 8-foot-long Champsosaurus fossil in the Cretaceous Arctic is puzzling to scientists from a uniformitarian perspective, because this species could not migrate or hibernate during the winter like some dinosaurs or turtles. The presence of Champsosaurus here implies that the climate must have been tropical to subtropical, with warm season temperatures ranging from 77 to 95 degrees Fahrenheit and the coldest monthly average temperature around 42 degrees Fahrenheit. This is in complete contrast to the current annual average temperature of -4 degrees Fahrenheit for this region. The existence of Champsosaurus shows that the ancient Arctic temperatures were warm enough to support ectothermic reptiles that neither migrated nor hibernated, highlighting the incredible climate difference between the past and present. The Cretaceous Arctic was not a barren, icy wasteland as we often think. Instead, it was a world of unexpected prehistory, a thriving temperate forest ecosystem where life flourished and diversified despite the unique challenges of extreme light cycles and cold winter temperatures. The climate significantly warmer than it is today, with high CO2 concentrations, created conditions that allowed lush forests to grow all the way to polar latitudes, where today there is only permanent ice. The discoveries of Edmontosaurus and Pachyrhinosaurus migrating in huge herds, Troodon with keen eyes and larger size for hunting in the polar night, Nanuqsaurus, a miniature T-Rex adapted to scarce food sources, the tiny marsupial Unuacomis huchisoni, surviving underground, or the ancient birds that nested in the polar region all paint a vivid picture of the extraordinary resilience and adaptability of life. Even ectothermic reptiles like Champsosaurus thrived here, indicating that temperatures were warm enough to support them. The ancient Arctic ecosystem is a powerful testament to Earth's ability to change its climate and landscape significantly throughout geological history. Studying these prehistoric paradises not only enriches our understanding of the past, but also provides valuable lessons on how life responds to large-scale environmental changes. In particular, the Cretaceous-Paleogene KPG extinction event about 66 million years ago, caused by an asteroid impact, ended the age of dinosaurs and completely changed global ecosystems, including the Arctic. After this event, the Arctic ecosystem, like other regions, underwent a period of recovery and restructuring, paving the way for the rise of mammals and birds, the groups that dominate modern ecosystems. Studies on this recovery process provide deep insights into the resilience of ecosystems after major disruptions, a topic that is extremely relevant in the context of current climate change.